Hello everyone. I welcome you all to this NPTEL session of finite element method. This is I'm Nikhil Gupta, research scholar from the Department of Civil Engineering from ISC Bangalore. So so we have covered till now 11 classes. This is the 12th week class and this is the last class of this course. So let's start this class. Okay. So I'll discuss the questions. Okay. So I'll start the questions for this week. The first question I have selected is uh, explain the axisymmetric problem. So till now, what you have understood in class, two cases has been discussed, which is one is plane strain, one is plane stress. So the third specific type of problem which you will be getting in the questions is axisymmetric problem. So let's discuss what it is. So let me show you the cases which you have understood till now. The first one is plane stress. So till now you all know the plane stress case, the thickness is very minimum. T is very minimum. Similarly, in case of plane strain, we know that the element or the object have a long length, so that thickness we take it as 1, and this is known as plane strain condition. So accordingly we make some assumptions and make our problem simplify and use it for our solution. Now what happens in case of axisymmetric problem? So in axisymmetric problem we have a object which is if you see at the different angles, it gives us the same geometry. So let's assume this as the top view and this is a center point of it. So whenever you see a theta, it is same, the geometry is same here also, geometry is same here also. So this is known as the axisymmetric problem, and when you make it into xy coordinate, it will look you like this. Which will be theta and r. So just a representation of it. Now I'll recap the plane stress and the plane strain condition, the value of the stiffness what you have computed in the class, which we generally known as the D matrix, which is sigma is equal to D into epsilon in case of single variable. Now for 2D case, for plane stress, we have studied sigma xx, sigma yy, tau xy, which equals to E upon 1 minus nu square, 1 nu 0, nu 1 0, 0 0 1 minus nu by 2, and here comes epsilon xx, epsilon yy, and gamma xy. So this you have done in class. Similarly, one more thing which you have done in class for plane strain. So what you get in plane strain is sigma xx, sigma yy, tau xy, and the d value changes like this. So you can go through your notes again and recap of this I have given here. Now same things I'll show you for axisymmetric also, what we get in case of axisymmetry. So now, since you're not working in xy, you are working in r theta coordinate system, so the stress values will be sigma rr, sigma zz, sigma theta theta, and tau r z. So I'm writing direct value. Now the vector will be epsilon xx, it will be corresponding to the sigma epsilon z, epsilon theta theta, and gamma r z. So this is basically the D matrix which we need to compute the values of sigma when we had the strains of it. So the coordinate system, to clarify it, if this is a point, this will be r theta z. So if you see in the top plane, it will be theta, this will be r, and the stresses which will be acting will be sigma rr in this direction, sigma theta theta in this direction, which is the what you say it as hoop stress. Then tau rz will act like this, and one force will act in this direction, which is the outward to the paper, which will be sigma zz. So these are the approximation we'll take in the 3D problem to make it simpler for the case of axisymmetry. Now one more thing to take care in this problem is how to represent the load vector. Now load vector, what you have seen in previous problems, is like this. I hope you all remember this. Now let's assume body force here and then write the problem. Now this will be area, and transpose will remain same. This will become bx, this will become by, and this will become tda. So it is obviously to understand this how it is happening. So the differential we have broken into tda. So this can be simply done and solved. So now let's take another question. So now my next question is, discuss the behavior of constant strain triangle for pure bending case. So what is a pure bending case? Let's assume this is a beam. Now for pure bending case, here M is at, yes, it is. So this is a pure bending case. No other force is acting on it. Now we have to see if we take constant strain triangle to model this beam using FEM, what are the results we will get? So let's start with modeling with one element in a height. So let's take this as one of the element. Now let's make the marking so that it will be easier for us to the problem. So this, let's say this is X, let's say this is Y, and this is C, this is C, and here it is L, here it is L, this is 1, this is not the node, so this is 1, this is 2, and this is 3. Now okay, for a beam subjected to pure bending, the solution from theory of elasticity will give so these are the solution which we get from the solving the problem from theory of elasticity. Correspondingly, epsilon xx, what we can see, u bar cl y epsilon yy as minus nu u bar cly, and gamma xy is 0. So these are the answer we are getting. This is the exact solution. We haven't used any element or FEM problem here. Now let's see the to see how CST represents these bending strains we impose on CST nodes. So we'll impose these node values in the CST element. So at node 1, x is L, y is minus C. So u1 will become minus u bar, v1 will become u bar by 2d minus L square minus nu C square. Now at node 2, where x is equal to L and y is equal to C, u2 equals to u bar and v2 equals to u bar by 2cl minus L square minus nu C square. Similarly at node 3, where x is minus L, y is 0, u3 will become 0 and v3 will become u bar by 2cl. So what we observe from this, we can get epsilon from also from this as well. So if we use the relation and get the epsilon, what we'll get? We'll get epsilon xs as 0, epsilon yy is 0, and gamma xy equals to 1 upon c minus nu c 4l square u bar. So this is the FEM solution using 3-node triangle, which is CST element. So what do you observe from this? As the name say, that constant strain triangle, so we see the some of the strains as 0, but in real problem, when we have solved the exact solution, they are not 0. So this, we can conclude from this that clearly these strains are quite different from exact solution. Thus, CST element is poor in bending. However, CST element can still be used for bending provided many elements through the depth. So what does this mean? So since we have taken only one element here, it was behaving too poor. But if we want to use the same CST element and want to refine our results, what we have to do, we have to make too many elements across the depth so that the result is less prone to error. I hope you have understood this. The solution I have written directly because I think you can do it now. And also the main purpose of this problem was to compare the results of both. So I have shown it directly. Okay. Let's go to the next question. So the next question I'll be taking is, okay, let's do this problem. Let's discuss the characteristics of Jacobian. Okay. So where do we need a Jacobian? When we are calculating the K matrix, it is required. So the triple integration from -1 to 1, -1 to 1, and -1 to 1, then B transpose D, B, then determinant of J, then D psi, D neta, and D neta. Okay. Now with that we know B is dn by dx, or we can write it as d psi I by dxi and dn by d psi, and this can be written as j inverse dn by dz. So this is a polynomial function of psi theta. I hope this is the clear to everyone. If we take a 2D case also, I'll write there for that also. In 2D, what matrix it will form? The J matrix will be del x by del psi, del x by del neta, del y by del psi, and del y by del neta. Okay. So we are checking the characteristics of Jacobian matrix. So what we can write, since J inverse is required for evaluating the K matrix, which we have observed here, we require J inverse. Determinant of J should be non-negative. At every point sin eta in master element. So what can you uh, counter to this statement? Think about it. I'll give you 2 minutes. What not seems correct about this statement? Okay, so to counter this statement, we can say we are doing a inverse. So while solving inverse, determinant J should not be equal to 0. By what the statement is saying non-negative. Even if the determinant is negative, we can still get the inverse. So I'll clarify that also. Actually, that is the next thing, next characteristics of the Jacobian. So they have combined both this statement and written it in one. So okay, let's take an example and understand this. Okay, let's take let's take this elements. So let's make this. Okay, this is your element. Then uh, this is 2. This is 3. This is 5. So this is one domain. This is second domain. This is third domain. This is 5. Okay, actually I'll draw it again. So this. Okay, so this is a coordinate system. So this is 2, this is 3, this is 5. Here it is 2, here it is 3, and it is 5. Okay, now this is domain 1, this is domain number 2, and this is domain number 3. So 3 elements are there. Element 1 and element 3 are convex domain, and element 2 is non-convex. So let me first discuss what is convex and what is non-convex. So if you see, element 2 is not a convex, not in convex domain because the line segment joining points 2 comma 0 and 5 comma 3 means point this and this. If we join a line segment, it will be like this. So it says does not lie inside the element. So what we can conclude from this, any element which has an acute angle like this, if you want to connect any of the vertices with another, you will get a you will get the line inside it only. This is this. Now if you take uh, like the same one all again, you see if you can join this, it will be outside. So a simple method to check whether the domain is convex or not, you have to connect all the vertices, and if all the lines are inside the element, then it is a convex. Otherwise, it is not. So what problem occurs when we have a non-convex matrix? We have to see that. So let's calculate the uh, Jacobian. So we know x is ni xi and y is ni yi. Now you know what master element will be, what here equations are. So I won't take spend much time in elaborating that. I'll write directly. X if you solve you will get 1 plus xi, and y if you will solve you will get 1 plus neta and 2 minus half of psi. Now to write the Jacobian, you will have 1 0 minus 1 by 2 1 plus neta and 2 minus half of xi. So when you solve the determinant, you will get half of 4 minus psi. So what we can observe from here, for any minus 1 to 1 as xi, Jacobian is positive. So this all we were doing for element number 1, which is this. So since it is convex, you are getting like this. So transformation is continuous and differentiable. Now let's take element number 2, which is non-convex. Okay, let's see what problem will occur. I'll draw it separately for better understanding. Now this is 1, 2, 3, 4. I have taken node numbers like this. This is 2 comma 0. This is 3 comma 2. This is 5 comma 3, and this is 2 comma 3. Okay. Now transformations you will again do with the master element, and what you will get, 3 plus xi plus neta by 2 plus half xi neta. Similarly, y will be 2 plus half xi plus neta minus half xi neta. So these are the two transformations. Now let's get the Jacobian. So that will be 1 plus neta by 2, 1 half of 1 minus neta, half of 1 plus psi, 1 minus psi by 2. So after solving it, you will get j is equal to 3 by 4 1 plus neta. Yes. Now what you observe, you have this and you have this, the master element. Now if you see, you will draw this line which is xi minus neta minus 1 equals to 0. You will get here negative. So this is the same part of this. So the Jacobian is not non-zero everywhere in the master element. It is 0 along the line xi equals to 1 plus theta, shown by shaded area. Now this area is mapped into shaded area in element 2, which is outside the element. Thus what we can conclude here, thus element with any interior angle greater than pi should not be used in any FE mesh. So now you got the answer why we should not use the convex uh, numbers, convex element in the during the FE mesh. Now you might remember one statement I gave in the starting, why the Jacobian can't be negative. That answer is still not, that question is still unanswered. Now I'll show that with another example. Let's take the third element like this, which is 1 2 3 4. I'll write the coordinates. Okay, now let me know what mistake did I did here. So what I did, I numbered the coordinates in the clockwise direction. The previous class also I have discussed that the numbering should be in anti-clockwise direction in order to avoid area of the element to be negative. So let's see what happens if we write it in clockwise direction. So transformation, again I'll write for this element number 3. So it will become x equal to 3 minus 1 by 2 xi plus 2 neta plus half xi neta. Then okay, 4 plus xi as the y. Now Jacobian will be modulus of minus half 1 minus neta 1 2 plus half of xi, and this will be 0. So when you solve it, you will get minus of 2 plus half xi, which is negative for minus 1. Okay, so what we can conclude from this, the negative Jacobian indicates the right-handed coordinate system is mapped with left-handed coordinate system. So this is clearly not acceptable. So such transformations should be avoided. So I hope you have got the answer to the statement why the Jacobian should not be negative, and also why it should not be zero as well. So the mapping you are doing should always be adhere to the characteristics of Jacobian, that it should be greater than or equal greater than zero, means non-negative. So let's go to next question. Question number 4. This is not a big question. So okay, what do you understand by geometric isotropy of elements in FE mesh? Okay, so we have to discuss what is the meaning of geometric isotropy of the elements. So let's start. So the definition says, the characteristic says isoparametric elements are geometric isotropy have meaning the numerical value of coefficient in K matrix does not depend on whether element is numbered as 1, 2, 3, 4 or 2, 3, 4, 1. So what does this mean? Let's say this is the element. We can write 1, 2, 3, 4, or we can write 2, 3, 4, 1, or we can write 3, 4, 1, 2. So all this will give you the same result, but keep a check that the numbering should be in anti-clockwise direction. Otherwise what will happen? The Jacobian will become negative and you won't get the proper results. So this is the meaning of the geometrical isotropic property of the FE mesh elements. Yes. Let's go to next question now. Okay, let's do this question now. This is question number 5 for today. So calculate the nodal load vector. Okay, so you have done many questions related to this. What new thing about this question will be that it will have a 2D element. till now we are doing with the 1D element. So let's take this element 1 2 3 4, and loading let's take like this, since ty, and in both directions let's just take this is tx. So we have tx and ty. So on edge 3 and 4 only this load will be distributed. So at that level neta is plus 1. So we'll quickly write the value of shape function at each node. So it will be 0 here, n2 will be 1 by 4, 1 plus xi, 1 minus neta, which will also be 0. N3 will be 1 by 4, 1 plus xi, 1 plus neta equals to 1 plus xi by 2. Then N4 will be 1 by 4, 1 minus xi, 1 plus neta equals to 1 minus xi by 2. Okay, so I put neta plus 1 for the shape functions. We all know the load vector of the element is given like this. Now you have ds uh, due to area. So what you can do, you can write it as TDL and do a line integral for this problem. So what DL will be, it will be dx whole square plus dy whole square. This we have already studied in the mathematics. So dl by dxi will be dx by dxi whole square plus dy by dxi whole square. If you write x, so directly I am writing 1 by xi by 2 of x3 plus 1 minus xi by 2 x4. Since we have to give the values in the equation, so dx by dxi will be x3 by 2 minus x4 by 2, or we just write it as x3 4 by 2 just for consideration. Similarly if we write y dy by dxi, it will come at y3 4 by 2. So now let's substitute the value in dl by dxi. So it will become x3 whole square by 4 plus y3 4 his square by 4 will become half of x3 4 whole square plus y3 4 whole square. Now you can summarize it as half of L3 4. So you can write dl as half of L3 4 dxi, and when you put it in load vector, it will become half of L3 4 minus 1 to 1 n transpose T dxi. So this is the final value of the your problem, that will be L3 4 T minus 1 to 1 in terms of shape functions. It will be like this. Txty and that to dxi. So you know all n's, so you can get the value of nodal load vector from this equation. Let's do this for concentrated load as well. Let's take question number 6 and do with a the full problem. So this is 1 0 comma 0, 2 6 comma 2, 3 6 comma 6 and 4 1 comma 5, and one load is acting here as 10 kilonewton, one is acting 16 kilonewton. Okay, so what you will do here, you have to get the nodal load vector, simply n transpose f. So xy is this, where you have to calculate, which is 4 comma 5. So this is 4 5, which will be equal to n1 0, n2 0, n3 0, n4 0, then 0, n1 0, n2 0, n3 0, n4, and here it will be x1 y1, x2 y2, x3 y3, x4 y4. Okay, and we'll substitute the value in functions of xi and eta, which will get 16 is plus 30 equals to 13 plus 11 xi plus neta minus sin neta, and other equations will be plus 9 neta minus sin. So when we solve that both the equations, we'll get xi as 0.2216, neta as 0.7216. So for this, when we calculate the n1 and 2, we'll get 0.541, n2 as 0.085, n3 as 0.5257, and n4 as 0.335. So final load vector will be rx1, ry1, rx2, ry2, rx3, ry3, rx4, ry4. Then it will be n1 0, n2 0, n3 0, n4 0, 0 n1, 0 n2, 0 n3, 0 n4. Then it's a 10 and 16, which is acted externally. So when you multiply the full values, you will get 0.54, 0.86, 0.85, 1.36, 5.2, 8.41, 3.35, and 5.36. So this is a solution for the load vector for the concentrated load. It was a little fast, but I did it so that you can understand how it is happening. So that's all I have for today's class. So since this is the last class, be prepared for your exam. Good luck for it. If you have any doubt, do send me a mail. I'll reply to it. Thank you and bye.